out of battery. There's only like a 6 feet radius where I can walk through today. All right, we're going to start right on time. So we'll continue our conversation about data path components, finish up the discussion about decoder and encoder, and then we're going to move on to sequential elements. We've been talking about combinational circuits for so long, and finally, we're moving to a new topic. All right. So starting with decoder, encoder. Again, let me switch my presentation device. Just 1 second. Yeah, any questions before we start about anything? Yes? I guess no, just call me Leon. Yeah. Well, sorry, technical issue. Let me try to figure out. Perfect. All right, so this is a decoder that we saw from yesterday. Here it goes. So a decoder has an input, 2 to the n outputs. It's essentially a way to generate all the minterms. We'll send in the 3 inputs. They will represent a binary number, and the corresponding index will be a 1. So essentially, among all these outputs, one of them is a 1, all the others are zeros. That is also called a one-hot encoding. So one of the multi-bit binary vector is a 1. It's called a one-hot. And implementation-wise, you can implement this as a bunch of product terms, right? Each output is a product function. So just you can put down 1 AND gate for each output. You have 8 outputs, you need 8 AND gates. You have over there 10 outputs for 4-bit inputs. You would put down 10 AND gates. All right. And we can use this component to build our error correction circuit, a connection to what we learned in week 1, I suppose. So error correction circuit takes a 7-bit message that the receiver received, and then we're going to do some processing to produce a correct 4-bit message. Right? I have to think for a second. How do you think we can implement this logic? Right? The goal is really to, for one thing, calculate those correction equations, and then use the correction code to find out one index to make the correction. So think a little bit how you would implement that circuit using decoder. Again, 7-bit input, do some processing to calculate the correction bits, and use the correction bits to find out one index to make a correction. Right? That's what we need for error correction. Yeah, any ideas? Anyone? Yeah, Mitchell, what do you have in mind? Or you can say I'm still brainstorming. Yeah. Clayland, any idea? Like how we start this design project using decoder? Yeah, we use a 3 to 8 decoder. And you see, we need to build in some additional combination logic to make this conversion, right? To glue different components together. For one thing to make correction, I need to compute from this 7 message bit. Right, I need to design some combinational logic to calculate my C0, C1, C2. Right, that one will tell me the index of the erroneous bit. All right. So let's say if I do that and I connected these 3 correction bits to my decoder. So now I would have a one-hot representation at the output. So one of those bits will be a 1, indicating the error position. Right. So let's say I want to correct my message. So if error happens at position 7, right, I want to correct it by connecting my M0 with the 7th output from the decoder. Right, so M0 comes from the top. I'm just omitting that long wire by just putting down the variable M0 over there. So if you have an error at position 7, then the correction word will indicate position 7, and this will be a 1. So if you have a 1 here, use an XOR to make the correction to flip the M0. You get the correct M0. Right. Similarly, if you want to correct M1, that happens at position 6. So you connect this with M1, send it to the corrected M1. And you just have to put down 2 additional XOR gates. So M2 happens at position 5. So minterm number 5 together with M2 gives you the corrected M2. And so on. Do the same for M3. All right. What we have just done is we use this component, the 3-to-8 decoder, to build out our error correction circuit. First, with the 7 bits, compute the 3 correction bits. Use the 3 correction bits to find out the right index, and then use an XOR to flip the erroneous bit. I have another exercise for you. So let's say if I want to implement a circuit using a decoder and a NOR gate. With an OR gate, it's very easy. These are minterms. You just collect all the minterm, the indices for the minterm from that minterm expansion, and then that implements the function. What if I give you a NOR gate? Could you implement this function using decoder and NOR gate by only adding some connections? You can think about it for yourself. And if you have any idea you want to share with us, just feel free to speak up. All right, this is my function f. And I want to implement that at the output of the NOR gate. What do you mean by flipping stuff in the K-map? You could flip the numbers. So you're saying that we create the complement K-map. So do you want to flip all the numbers? Yeah. OK. So I'll create a complement K-map 1, 0, 0, 1, 0, 0, 1, 1. This is really the K-map for F complement. All right. And then what do you do with this flipped K-map? Yeah, you can find the minterm space on this. So that's minterm index number 0, 1, 2, 3, 4, and 5. Minterm 0, 3, 4, 5. And what we can do is we can essentially, at the output of this OR gate, we implement f prime, so that after inversion, we get back to our original function. So we can connect minterm 0, minterm 3, minterm 4, minterm 5 to the NOR gate. Essentially, to an OR gate, we're implementing the complement of f. So it's a NOR gate, we're implementing the original f. Similar to what we did with that singular max term from yesterday's example. Right. Or the other way to think about it is really there's an equivalent where you can think of this NOR gate as an AND gate with inverted inputs. So every minterm becomes a max term. You're essentially collecting the indices of the max terms to construct the function. Any questions? Right. Again, decoder gives you all the minterms. We generally collect those minterms using an OR gate to implement function. But in these alternative forms, with a NOR gate, you can collect sort of max terms, or you can implement the opposite of the function. For this Hamming code correction example, essentially we do some additional combinational processing before and after the decoder to calculate the correction bits and then make the corresponding correction using an XOR gate. So the opposite component of an encoder is of a decoder is called an encoder. So decoder has 3 inputs, 8 outputs. An encoder will have 8 inputs, 3 outputs, or 4 inputs, 2 outputs. So essentially 2 to the n inputs and n outputs. An encoder assumes that the inputs is again a one-hot encoding, so a singular one among all these bits, and then the output will represent the index of that one input value. So if you have an input 1 at position 3, output will appear as 1, 1. If I input 1 at position 1, output will appear as 0, 1. It tells you the index of that one input at the data inputs of the encoder. All right, get the index of the only input whose value is a 1. So this is really the opposite of a decoder, but this one has a few limitations. Oh, sorry. Number one, you cannot handle multiple ones at the inputs. That violates the constraints of having a single one. And therefore, the output of the encoder is undefined. The other issue is that if you have no one at the input, you have like 0, 0, 0, 0. Again, decoder doesn't really have a way to represent that scenario. So we sort of put that as an XX, an incompletely specified condition. We don't know what will happen. And these two problems can be addressed by adding in one additional output, valid. That will be one only if you have at least a single one at the input. So if you have an all 0 input, valid will be 0 to tell you that you don't have any one. And also, we're specifying a priority on these positions on the input data. So now if you have multiple one of them at position 4, and the other, let's say, at position 6. Right here, I have two ones. It's going to do a tie breaking by following a particular priority tool. A particular priority rule. So in this case, this is a, let's say x, y4 and y6. If y6 is 1, if you look at this column, output is directly set to 1, regardless of the other lower input bits. So y2 has higher priority than y4. Right? Similarly, if you have a 1 at position 5, regardless of what happened on the other lower bits, output corresponds to position 5, so 1, 0, 1. So really, this priority encoder gets the index of the most significant input whose value is a 1. So the input bit with a higher index has a higher priority. And this allows us to break a tie in the presence of multiple ones at the inputs. Any questions about this component? Right, this is a new way of representing the truth table by putting down some don't cares on the inputs, just essentially a more compact way of enumerating all those input conditions. Right, this really means for all the values over here, as long as I have a 1 at position 7, it's going to set the output to 1, 1, 1. This idea of encoding in general has a lot of engineering applications. So encoding is a way to convert parallel data into a serial data. It's also a way to convert sparse data into a dense data. So for example, when you send out a message, if the message has a lot of zeros, you can do an encoding to compact it to a lower bit width to reduce the communication bandwidth. Even we can use the idea of encoding and decoding to implement the neural network. This is called an autoencoder structure, where through encoding, we can extract essential features from some input data. And through decoding, we can convert this compact representation into some more descriptive features. Has anybody heard about this architecture, like autoencoder in machine learning neural network? Yeah, it's pretty popular nowadays. And what we learned is essentially just a simple binary encoding decoding idea based on the number of ones. For decoder, we have a 1-hot encoding at the output. For encoder, hopefully we have a 1-hot encoding at the inputs. But if not, we have a tie-breaking mechanism through this priority encoder so that the output remains valid. So that's everything about the data path components. We have seen multiplexer, which is essentially a way to apply Shannon's decomposition theorem to implement function. We have seen encoder and decoder. And you can usually use decoder to implement functions because that gives you all the minterms, and minterm expansion is always a way to implement function. With encoder, you can hardly use this to implement function. This is more used as an analysis component. You cannot generally use it to implement like an arbitrary Boolean expression. All right. So with that, we're going to move on to sequential circuits. Right. We spent 3 weeks on combinational circuits. And finally, this is something entirely new. Or not entirely, because they still depend on Boolean algebra, still depend on these gates, and we still need to build combinational logic within sequential circuits. In lecture 1, I showed you the distinction between combinational and sequential systems. Combinational system output depends on only the current inputs. When I change the current inputs, output gets updated. For a sequential circuit, outputs depends on the current inputs and some information regarding the previous inputs. So the history of what you have applied at the inputs will affect the output results. It doesn't mean that I'm memorizing all the previous inputs. It might just generate a very complex signature based on the previous input. But with some previous information, that allows you to tremendously increase the representational power of the system, to be able to expand the capability not only by putting down more inputs, but also by running the system for a longer period of time. For combinational circuit, these are the kind of circuit diagrams that we have seen, and all of them are direct acyclic graph. These are directional graph. Information flows from the inputs to the outputs. And sometimes people even put down a small little arrow showing the flow of the data. It's also an acyclic graph. There's no cyclic structure, right? Things go from this direction to the other direction. There's no back edge. So this is a direct acyclic graph. And that is true for two-level circuit and also for multi-level circuit. So to build sequential circuits, we do need combinational feedback, a way to bring back some of the previous information back to use. And there are several ways you can attempt to build this feedback. The first approach is to take a single inverter and then connect the output to its own input. Now you have a feedback, and data can flow within that singular inverter again and again. But because it's an inverter, if the output is 0, next cycle, output is 1. Right? After a little while, after another gate delay, output becomes 0. After another gate delay, output is a 1. So the output behavior is represented by that waveform. Oops. Where this really corresponds to the gate delay. After every gate delay, the output flips between 0 and 1. So that is a sequential circuit, sort of. Like, the output of the gate depends on, like, not the current inputs, but some of the history information about what has happened before. But it never stabilizes. So it's not of any significant use. So the second idea is to put two inverters back to back. And this actually allows you to get a stable behavior. So let's say, based on the first picture, the output of the first inverter is a 1, so 1 goes to the second inverter, becomes a 0, 0 comes back. So these two inverters can stabilize at this condition. They can also stabilize at the other condition. If you start with a 0 over here, so 0 becomes a 1, 1 becomes a 1, come here, becomes a 0. So again, it stabilizes. It's going to settle down in one of those two conditions, depending on what is your original, the initial condition, when you just turn on the power, right? You connect the device to a battery. All of these devices will receive some arbitrary initial value. And depending on what happened, which is out of our control, it will settle down to one of these two conditions. So it stabilizes, but you have no way of controlling the value. To address that problem, we can put down two NOR gates, again, back to back, and control them with two different input signals. And then we'll see what will happen in this circuit is that, let's say if you put down a 0 and 1 over here. 0 will directly control the NOR gate output to a 1. 1, 1 gives you a 0. 0 cycles back, and then gives you an output of the NOR gate, a 1. Right. Oh, sorry, I think I should start from the R signal. So 1 is the dominating input value to a NOR gate. So 1 will set the output to a 0. 0 comes back, 0, 0 gives you a 1, 1, 1 gives you a 0. So this device stabilizes at this condition, Q equals 0. Right. So I just described this bottom condition, S equals 0, R equals 0, Q equals 0. If I change it to S equals 1, R equals 0, the first NOR gate will produce an output of 0. 0 NOR 0 gives you a 1, 1 comes back, gives you a 0. So that's another stable condition. S equals 1, Q equals 1. And now if you set both of them to 0, we essentially get back to that previous scenario. You have two inverters back to back. Right? 0 essentially converts the NOR gate into an inverter. 0 converts a NOR gate into an inverter. So you have that two inverter picture. So data gets to be stabilized based on the previous condition and continue, like remain in that device even after we have spent many seconds or many nanoseconds, let it run. It will remain at the previous value. This is the idea of a set reset latch. This is really the same picture as before, but now I'm just putting them in parallel, which is a more common representation. Same as before. The first picture, R equals 0, S equals 1. I'm highlighting some of these signals in yellow. These are like the signals with a value of 1. So 1 gets the output to 0, 0 goes back to top, produce an output of 1. 1, 0, again, 1 goes to the output of 0 at Q, Q comes back at the bottom, 0 nor 0 gives you a 1. 1 comes back to the top, it doesn't change anything. And finally, if you have both inputs being zeros, both of those NOR gates are converted into inverters. And what's going to happen is that the signal on the top, I'll call that the Q value, will flow to the bottom, going through that inverter, becomes Q prime. Q prime will circle back to the top, and going through the inverter or a NOR gate with a 0 input, it's going to become Q. Right? And Q is a variable representing the previous value on the Q signal. So whatever I had over there, whether it is 1 or 0, it will remain at that value indefinitely, as long as my R and S, both of those inputs, are 1s. Right. And with that, I'm going to show you a demonstration on our favorite platform, Circuitverse. All right, so what I built over here is a combinational circuit and a sequential circuit. So this combinational circuit is a two-level circuit, AB plus BC. And as you see, you can play with the inputs and then under different conditions. Let's say this is a condition producing a 0. This is a condition producing a 1. You can change your input, and the output will respond to your input change. On the right side, I built an SR latch, what I just showed you on the slides. Two NOR gates with this feedback connection and controlled by different inputs. So if I set R to be a 1, S to be a 0, 1 going through a NOR gate makes Q a 0, Q comes back to the bottom, makes the output a 1 for Q prime. This device stabilizes at a condition of 0, 1. If I change it to 1 at the bottom signal will be a 0, the top output will be a 1. Right? That's when Q becomes a 1. But you see, take a look at this condition and try to remember it. Both of the inputs are zeros, the Q output is a 1. Right? Both inputs are zeros, Q output is a 1. Now take a look at this. Both inputs are zeros, the Q output is a 0. Right? And I did some flipping of the input variables, and now I get a different description of the output. The output depends on not just the current inputs, but also what has happened before. So depending on what happened before, under the input, 0 input, I could have a 0 at the output. I could have a 1 at the output. And that is the definition of a sequential circuit. All right. Yeah. Any questions? Well, just verify that with the 0, 0 input, sometimes you get an output of 1, sometimes you have an output of 0, and that depends on what has happened before. So this is a sequential circuit. And finally, I have never shown you what happened in the 1, 1 case if I put 1 to both of those NOR gates. And that's actually an invalid case. Does anyone know why it is invalid? Right? What happens if I put 1 to both NOR gates? Yeah. The output becomes 0. Yeah, this is a 0. The bottom one is also a 0. Do you think that's invalid? Why is that? Yeah, we set these variables to be, they should be complement to each other. We call this Q prime. So they better be complement to each other. In all of those previous cases, right, they're complement as two concrete binary values. And over there, they're complement to each other based on this variable Q, essentially the state from some previous execution. And over here, we get 0 on both Q and Q prime. And if Q and Q prime actually carry some meaning, that is an invalid condition. Right? But here's what actually makes it invalid. So after that, if you change it to 0 and 0, so you apply the 1, 1 input, set both Q and Q prime to 0, and you change it back to 0, 0. 0, 0 is typically a condition that allows you to hold the previous value. Right? But take a look at what will happen in this situation. So 0 will come back to the bottom. These two will be 0. Right? The output from Q and Q prime will flow back to the input of the NOR gates, which essentially sets the output to be 1, 1. And those 1, 1 will circle back to the NOR inputs, set the output to 0, 0. And this will just repeat forever. 1, 1 becomes 0, 0, comes back to the front, becomes 1, 1. And it never stops. So you run into an unstable condition after using the 1, 1 inputs and then switching that to the 0, 0 input. When Q and Q prime are not complement to each other, you cannot reasonably hold it. And that is a danger with them being non-complement to each other. And therefore, with an SR latch, those three conditions are valid use of the latch. The bottom condition is an invalid use, because we might run into some indeterminate behavior afterwards. Right. So I just demonstrated this component on CircuitVerse. Again, two NOR gates building a latch, and then you can also play with it by going to the link above. So latch is the first memory device that we saw. And it was invented in 1981 by some British physicists using two vacuum tubes. Does anyone know what vacuum tubes are? These are two vacuums? Yeah, I don't know. I don't know what they are. But I know that's what people used to build circuits before transistors. So you see, Boolean algebra is about like 30, 40 years before this. And the use of Boolean algebra for designing digital circuits, invented by Shannon, was around 1938, so 20 years after this. So roughly before, I would say, 1940s, we don't have transistor devices. People built electronic circuits using vacuum tubes. And in the 30s and 40s, people started to use transistors, but those are still discrete transistors. And finally, after another 10, 20 years, like 1958, 1960, people start to put transistors in a single chip. And that's when we get the integrated circuits. But you see that diagram. This is a pattern diagram from 1920, right, by those people. And they have these two devices, and they sort of have some connections between them, forming like a combinational cycle, a back-to-back connection of two vacuum tubes. And that's probably exactly what we did with our two NOR gates. And this latch was later used in Carlos's computer to help with cryptanalysis. That's widely believed to be the first programmable computer and used to crack some of these coding schemes. The SR latch, a way to memorize the value by first setting or resetting it, and then use the 0, 0 input to hold the value. So these two signals, R stands for reset. We want Q to be a 0. We reset it to 0. S stands for set. We set it to 1, 1. And we can describe its behavior using a thing called characteristic table, which is no other than a truth table for sequential components. So SR00 is the hold condition. So the output depends on the previous output. It will actually hold the previous output. If R is a 1, we just analyze that will set Q to be a 0. So we call that a reset condition. 1, 0, set is 1. We set the output to a 1. 1, 1 is an invalid case. So that should never happen at the input of an SR latch. You can also draw the same truth table with one additional variable by bringing Q from the output column into the input column. So this is really a device whose output, the next state, the Q plus. Q in the next execution run depends on not only the current input's SR, but also the previous output Q. So you can think of Q as an input, and then put that at the input column of the truth table. And that's a different way of representing the characteristic table of an SR latch. Again, we can look at it by essentially looking at these two rows as the hold condition. So output is the same as the previous Q value. 0, 1 is reset. 1, 0 is set. 1, 1 never happens. So this describes the very same amount of information as that more compact characteristic table. I would say in general, we use that more often. And this is, if you want to put that into a circuit, you don't have to draw these two, interconnecting NOR gates. You can just draw a box and then put down S and R inputs. This is typically how we represent the latch in a circuit diagram. Yeah. Any questions? And I expect you to be able to do conversion between these representations. Starting from the implementation, you can put down those values 0, 1, 1, 0, 0, 0, and then follow through the circuits, do this execution until it stabilizes to derive the characteristic table. That table, you can also show that as a K-map, again, to represent the next Q value based on the current Q and the current inputs. And then you can also write the Q plus, the next Q behavior, in terms of these three variables as a Boolean expression. And that simply involves finding a representation from the K-map, like this is a prime implicant, this is another prime implicant, and these two together form the minimal representation for that function. And that's a way to describe the next state, Q plus, based on the inputs and the previous state. You see, here we're talking about combination of sequential circuits, but we're still applying some of the same analysis methods as we learned in combinational circuits to analyze the sequential behavior. Again, Q plus represents essentially the new Q value in the next execution round. Right? When you change your input value, you're going to get a new Q value. So Q plus stands for that new Q value. We often call Q like a state variable because you can memorize it. You can have it be at one state 0, for a little while. So we call that like state Q. Right? So to make sure that you can do this kind of conversion between the circuit diagram to the truth table and eventually to the equation and K-map, I want you to try out this exercise. So now I'm giving you a different construction of a latch with two NAND gates. We build the SR with two NOR gates. So I want you to plug in these different values into the latch and see what is the behavior of the latch. I'll give you 2 minutes to work on this exercise. Again, bringing all those 4 different input combinations to the circuit and to see what is my next state value. If anyone has completed it, just let me know, and then I'd like to come over and then check your work. You have another 25 seconds before we get into a group discussion. All right, time is up. Could you talk with people around you and then compare your work and then explain to each other how you think about this problem? I guess feel free to move around to discuss. Yeah, you don't have to really complete it for whatever you already got, like one example, two example. That's also perfectly fine. Mitchell, would you like to come to the other side of the classroom and then talk with them? Yeah, get them to talk. Can I see what you get? Or are you still thinking about it? Do you have any questions? Yeah, I like to do it with only like the smaller characteristic table without, by essentially compacting Q as part of the output and then describe it in terms of like Q or 0 or 1. That saves you a bit of work. Right now, I only have to try 4 different cases instead of 8. Yes. Yeah, I only use that table. I'll just set my A and B to be, let's say, 0, 0. And then I'll try to evaluate them through the gates. So 0 through the NAND gates, set the output to a 1. Right? 0 through the NAND gets the output of 1. Yeah, then it will be an invalid case because both of them are 1s. Right, so I only set A and B, and then I just let it evaluate forward. And did you also find the hold case? Yeah. What allows you to kind of remember the previous state? Yes, it is. Right. 1 makes those 2 NAND gates an inverter, so they get to remember what happened before. Mark, do you need any help? Yeah. So you see, with any input value you put into the latch, you have to evaluate both Q and Q prime, because sometimes it could be an invalid case. Right, actually, with 0, 0, the first case you tried, 0 makes this a 1, 0 makes the bottom output a 1. So in that case, both Q and Q prime are 1s, which is not a valid scenario. Right? That's essentially like the 1, 1 case with the regular SR latch. Yes. Not necessarily. If you have a 0 at the NAND inputs, that directly sets the output to 1. So 0 and anything is a 1, you complement it, 0 and anything is a 0, you complement it, you get a 1. Some of these values are so powerful that you can do evaluation independent of the previous state. Yeah, I'd like to start from with those cases first. Yeah. Any questions from this side? Yeah. Why is that?
Because
that's right.
It's gonna come out.
Yes. Yes.
This one.
So you're setting A to be a 1, the bottom one to be a 0 and 1. That's the input case you're trying to examine.
Okay, so 1.
So see, so 0 is very powerful. It directly sets the output to a 1. Right? 1 is a little bit weaker. It will propagate whatever happens on the other side. So you can call that a Q variable.
So 1 and a 1.
1 and 1. The previous value, yeah, 1 and 1, which is, that's right. Yes, yeah, that's right.
So 1 and 0.
So
That would be
you look at based on the Q variable.
set.
Yes. Yeah, you flip them, then Q prime gets set. Essentially, Q gets reset. Yeah, yeah, then. That's right. All right, guys, you have another 30 seconds to discuss before we do it together, and then I'll show you some of the tricks. All right, time's up. So you see, I showed you two different ways of representing the characteristic table, a more compact way and a more expanded way. In general, I like to use the compact table by not putting the previous date as one of the input columns. That reduces the amount of work. With this compact table, there are only 4 cases I need to try. So that's like the trick number 1, to try to minimize your work. And then I like to start with some situations where the input value directly determines the output of the gate value. So for example, for a NAND gate, 0 is the dominating input. It essentially overrides the other inputs. Well, once you have a 0 at the input, output will be a 1, regardless of what happened from the other side, essentially regardless of the previous Q and Q prime. And with 0, 0, I have both Q and Q prime being 1, so that is an invalid case. And then I'll move on to a different value. Let's say I have 0, 1. So when I put down 0, 1, I will start my evaluation on the 0 side. Again, because 0 is the dominating value for the NAND gate. So 0 can directly set the NAND output to a 1. And then based on that fixed value, I'll bring the 1 to the bottom. 1 and 1 is a 1. Complement that gives you a 0. So 0, 1 at the inputs gives you 1, 0 at the output. And because Q equals 1, that is a set condition. And similarly, if I want to try the 1, 0 input, I'll start from the 0 side. 0 sets my output to a 0. 0 comes to the top. 0 and 1 complement, which gives you a, 0 gives a 1 at the bottom. 1, 1 comes to the top. Complemented gives you a 0. And Q and Q prime are complement to each other. Q is a 0. So I call that a reset condition. And finally, I'm sort of running out of color. I'll use a blue. I have 1, 1 at the inputs. And this is the more difficult scenario. 1 doesn't directly set the output. So I have to bring back my previous state into the inputs of the NAND gates to do the evaluation. From the top to bottom, I'll just show that as a Q variable. And bottom to top, I'll show that as a Q prime variable. The previous Q and Q prime values. Q prime going through the AND gate with a 1 input gives you a Q prime, and after complement, that is a Q. I'm really saying that 1 and Q prime complement equals Q. I'm doing this kind of a symbolic or algebraic evaluation of the gate. If you don't like it, you can, of course, replace Q with 0, replace Q with a 1, and try both cases. At the bottom, 1 and Q is a Q, complemented, that gives you Q prime, which is essentially the same as before. And with that, we know that Q becomes still Q. Q prime remains at Q prime. And therefore, Q plus is Q, and that is my hold condition. Yeah, essentially a number of tricks. I'll just sum it up. Number one, use a smaller table. And in this 1-1 case, if you want, you can partially expand that case by using concrete values on Q. Q equals 0, Q equals 1, and triples. But I like to do this kind of symbolic evaluation. Number two is when you pick a particular input combination, start with the side that dominates the gate, so they can run the evaluation regardless of the previous state. And that typically helps you to simplify the problem. And the other thing is, at the end, you generally should have several different operations. Right? These are like pretty common operations: hold, set, and reset. And we'll see a few more types of operations in a second. Yeah. Any questions? I have a practice on this in today's workbook. A similar example, again, try to analyze a different latch design. There are just so many different ways you can design such a memory component. All right. So a latch reacts to its input change all the time. And that actually creates some problems. Let's say if we use a latch at the end of a combinational circuit, and let's say this combinational circuit has some static hazards. Static hazards in two-level can be avoided by including additional implicants or implicates. In a multi-level form, it's actually very hard to prevent. So let's say this combinational circuit has some static hazard. We're going from one 0 case to another 0 case. We'll momentarily produce an output of 1. And if that happens for my latch, I expect the previous condition to be 0, 0 to hold it. I expect my new condition to be 0, 0 to hold it. But if momentarily it goes to 1, 1, then it's going to raise all the problems. That's an invalid scenario. And it's going to cause my latch to work in an indeterministic way. So for that reason, we want better control of the latch. We want to be able to enable it when we need it and disable it when we don't want it to react to its input changes. And with that, we have a gated latch design. We take the original latch, we add some additional gating logic. So gating is a way to disable the component. So let's say we're adding one additional gate control input. If gate is 1, then both of these AND gates will behave like a buffer. They don't do anything. So S will go to S, R will go to R. Latch will behave like a regular latch. If gate is 0, I'm essentially disabling the component. 0 sets my S to be 0, R to be 0 to hold the previous condition. So even if my primary S and R input changes, they will not affect the operation of the latch because they have been gated out. If you look at it in terms of the truth table or the characteristic table, when gate is 1, it behaves like a regular SR latch. When gate is 0, immediately I can only hold it. So the latch does not respond to the input SR change anymore. And you can implement that using, again, many different ways. You can also implement a gated latch using NAND gates. Right? What I did earlier is I assume a NOR gate implemented SR latch together with 2 AND gates. And then when you apply some of those transformations, like De Morgan involution, multi-level bubble pushing, you can also implement that using this kind of a NAND behavior. And I invite you to also try it out. Try to plug in those input conditions, 0001, 1011, to confirm that this indeed works as an SR latch. All right. So SR latch supports 3 operations: set, reset, and hold. There's a different latch called a D latch that supports only 2 operations, set and reset. And with 2 operations, you only need a single input. We used to have 2 separate inputs, S and R, and you have to sort of enforce a particular relationship on those 2 inputs. And for convenience, you can also implement a single input latch by using D as your set input and using R as the complement of D. So with this new design, if D equals 1, S is a 1, R is a 0. Right? Assuming that the gate is 1, so the latch is enabled. So this will set the latch to a 1. If my input is 0, top 1 will be a 0, bottom 1 will be a 1. It's going to reset my latch to be a 0. So that is a reset condition. And then if I turn off the gate, set gate to 0, the SR becomes 0, 0. It will hold the previous value. Right. Okay, now I'm essentially achieving the same functionality with one less port. It's a bit of optimization. And in reality, we use this kind of D components, D latch, and later we'll see a thing called D flip-flop a lot more commonly than SR latch and SR flip-flop. And this design completely avoids that invalid case. There's no way that SR can both be ones, because they're really controlled by the same G and the same D inputs, right? And the complement relationship is enforced by the inverter. And we can also represent the behavior in the timing diagram. Remember this for combinational circuit. We can also analyze it for that single sequential component, where if gate is 0, output will just remain at the previous value. Even if you change the D inputs, output doesn't change. When you set gate to 1, you're turning on the latch. So whatever change happens at the inputs will be propagated to the output. So D is 1, Q is 1, D is 0, Q is 0, D is 1, Q is 1, D is 0, Q is 0. So output will essentially react to the input almost immediately, but this diagram is also showing a little bit of delay. So let's say there's a tiny bit of delay. You can show that in the timing graph by just offsetting the output response to the right by a tiny bit. And in this mode, this is also called a transparent latch, because once gate is turned on, it becomes transparent. Whatever happens on the inputs will be saved at the output. And when you turn off the gate, we'll just remember the most recent condition that happened at the output. All right. And in reality, circuits often work with a clock signal, whereby a processor specifies a clock frequency. And in fact, when you run any circuits, they will typically operate according to a central clock. And in real life, it could be multiple clocks controlling different parts of the circuits. So clock is an important concept. And in general, we want one round of computation to happen within one clock cycle. And clock cycle is defined as between one rising edge to the next rising edge, or one falling edge to the next falling edge. Right? The difference between two edges of the same shape defines the clock cycle. And the most common way of running sequential circuit is to spend that full cycle running some combinational logic, and at the end of the cycle, save the result to some of these memory elements. Right? So we want to spend as long as we can to do computation, and at the end of the cycle, we save it. And then we get into the next round, new computation, spend the full cycle, and save the result. So to achieve that kind of behavior, we need a slightly different kind of sequential component. The latch that we have just seen with that additional gated inputs, and if you connect gate to the clock, it will respond to input changes whenever your clock is 1. So when your clock is 1, that's the period of time when input change gets propagated to the output. But to be able to what I described earlier, to spend that full cycle doing combinational computation and only save the result at the end, you don't want your sequential element to respond that frequently. You probably want it to only respond at that precise moment when the clock changed from 0 to 1, and the next precise moment when clock changes from 0 to 1. You want it to respond at a much smaller interval, the exact moment when clock changes, so that you have the full cycle to run your combinational circuit. Right? And without having to worry about any glitches, any momentary changes that happen at the flip-flop inputs or the combinational circuit outputs. And this is a distinction between latch, what is so-called level sensitive. Right? When gate is 1, when clock is 1, it will be sensitive to the input change, versus a flip-flop, which are edge sensitive. So edge is a transition. The clock going from 0 to 1, that's called a positive edge. When clock goes from 1 to 0, it's called a negative edge. But if you only want a component to react at that precise moment, it's called edge sensitive. You can build these edge sensitive devices by putting together two level sensitive devices and letting one of them sensitive to like the negative value, like 0, and let the other one sensitive to the 1 value at the clock. Right. So we're putting together two D latches, connect them back to back by using different clock signals to control them. And this is a way to realize edge sensitivity. Right, so let's have a closer look about what is happening in this diagram. So let's say at the beginning, my clock is 0. Clock is 0, disables the first latch. Sorry, enables the first latch because there's an invert over here. Right, clock 0 sets gate to 1, so the first latch is enabled. Whatever happens on the input will get propagated to the Q output of the first latch. That happens when clock is 0. So clock 0, information will flow directly from latch input to latch output. And when clock becomes a 1, right, the first latch is immediately turned off. I really mean that at this moment, when clock goes from 0 to 1, suddenly the first latch is turned off and the second latch is enabled. So the middle part will remember the most recent D before the clock change. When your clock goes from 0 to 1, at that precise moment, the first latch gets disabled. So the output will go into the hold mode. It will remember the most recent data right before the clock edge. At the same time, because clock is a 1, the second latch becomes transparent. And therefore, whatever gets saved in the middle will be propagated to the Q output when clock equals 1. And that will happen for this half of a clock cycle until the clock becomes 0 again. At that point, second one is disabled. First one is enabled, so we're going to read some new inputs until the next positive edge of the clock. First one disabled, the value saved at the middle will be propagated to the final output. Yeah, any questions about this? The goal is to really design a edge-sensitive device by putting together two level-sensitive devices, but being sensitive to different levels. And therefore, a kind of contribution change will happen when your clock change from 0 to 1. And eventually, what this component does is it will only react to the inputs right before the clock edge. That input gets saved in the middle, and then it will be used for the rest of the cycle. You can also define the opposite level edge sensitivity. So what I showed you earlier is a flip-flop that will only react to the rising edge, going from 0 to 1. It's also called the positive edge. Right? It's going to the positive side. By changing the clock signal, you can easily flip this sensitivity behavior by making it falling edge sensitive, which means it will only react to your input data, the D input, when clock goes from 1 to 0. So these are the reaction time of the flip-flop. Right? Symbolically, you can put down like a box like this, and then triangle typically means a clock. And by putting down one additional bubble, you indicate that it will be sensitive to the opposite of the clock, which are falling edge or negative edge sensitive. Right? I guess this is what you really need, right? What is actually happening? Once you build this flip-flop, what will happen to my output behavior, depending on the clock? Right. So you have one clock, the main clock controlling the second latch. You have the opposite clock, so clock gets negated for the first latch. And what will happen is that when your clock is a 0, sorry, when clock is a 1, the first latch, let me see. Oh, yeah. OK, when your clock is a 1, when clock is 0, so G1, the clock received by the first latch is a 1. First latch will be transparent. So within this period of time, when G1 is 1, D will go to P. Right? Data will flow from the data inputs to that middle place. And when your clock goes from 0 to 1 on the positive edge, suddenly the first latch is disabled, and the second latch is enabled. So the p-value, take a look at here. P does not react to any change on D anymore. So P just maintains this value for that half clock cycle. And that's because the clock enable for the first latch is set to 0. So P just remembers the value that happens right before the positive clock edge. In the meantime, the second latch becomes transparent. So whatever value sits at P will be propagated to the final output Q. And that is because the second one, G2 equals 1. G1 equals 0. At the positive edge of the clock, first latch gets disabled so that it doesn't track the D input anymore. Second latch gets turned on, so these stable values sitting at the middle will be propagated to the final output. Right. And actually, if you forgot about these details, only look at the main clock, the data inputs, and the final output, I think you get to see a clearer picture. Forget about G1 and P, and let's see what is happening with the flip-flop. So I said this device will be rising edge sensitive or positive edge sensitive. So at this moment, I'll look at what is my data on D. And that data will be propagated to the Q output for the entire cycle. Right? If you don't worry about the internal details, you get a much simpler picture. At the next positive edge, again, what I care about is what is the value of D at that moment. And that at that instance, the low level will be propagated to P. Right? That's the overall, the high-level behavior of a flip-flop. It will only react to the data value right before the positive edge of the clock. Any questions about this? And these are the 4 flip-flops that we will deal with, and these are also the most common flip-flops. We have D flip-flops that support 2 operations, set and reset. So D0, reset, D equals 1, that is set T. We have an SR flip-flop, again, supporting the 4 operations just like before. So the definition of an SR latch and the SR flip-flop really identical, except that latch is level sensitive, flip-flop is edge sensitive. There's another flip-flop called a T flip-flop. T stands for toggle, I suppose. It supports hold and toggle operation. So this allows you to either hold the previous value or toggle it. 1 to 0, 0 to 1. So next Q is the complement of the current Q. And SR can be augmented into a JK flip-flop to handle that 1-1 case, to repurpose it as a toggle condition. So 1-1 now becomes a toggle condition. Your previous Q is a 1, now it becomes a 0. Previous Q is a 0, it will become a 1. So with this, again, I'm going to come back to my demonstration. And let me first set a slow clock frequency. I'll set a clock time to be 2 seconds. Right, so a D flip-flop. Okay, the bottom signal is a clock, and it automatically changes every 1, 2, 1, 2, every 2 seconds. Right. And I said this one will be edge sensitive. So it will only react to my input change at the positive edge of the clock. Right, I change my input, clock goes to 0, clock goes to 1. At that precise moment, output gets updated. Again, I'll change my D to 0, and when clock goes from 0 to 1, at that exact moment, output gets updated. Not update, and update. Right. So the output only changes when clock goes from 0 to 1. It will record the D value at that moment. So the second component is a T flip-flop. it will do toggle. So if you leave t as a 0, 0 is the hold operation. So at every positive edge of the clock, output remains same as before. If I set t to be a 1, flip-flop will toggle the output. So if I just let the clock run, it will toggle between 0 and 1, 1 to 0, again and again, indefinitely. Right? It will keep toggling the output. So let's say if my output is toggled to be a 1, and then I set t to be a 0, in subsequent cycles, it will hold the t value, the q value. Right? So the output stays at a 1. This platform doesn't have an SR flip-flop, so I'll just show you how the JK works. So 1-1 for JK flip-flop, JK adapts the 1-1 case to a toggle function. So 1-1 essentially behaves like a toggle. It goes to 0, goes to 1, we'll toggle it. Comes back to 0, goes to 1, it should toggle it again. Right? So 1-1 will keep toggling the flip-flop. 1-0 is the set condition. So JK essentially corresponds to S and R. So J is set the output to a 1. And if I make K a 1, it will set the output to a 0. Right? Just so happen to change the input right before the positive edge of the clock. And 0, 0 is the hold case. Current output is 0, it will just remain at 0. Right? Let's say if I set it to 1. All right, and then I hold it. Then my output will remain at 1. Right? So now even if nothing happened at the JK, the flip-flop is capable of memorizing the previous value. Yeah. I hope that the demonstration will provide you a clearer picture about how they operate. Again, they only care about the signal value at the inputs right before the positive edge of the clock. And then they support different kinds of operations. In general, hold, toggle, set, reset, like these 4 operations are the most common operations that we deal with. Any questions? All right. So now with that, I have an exercise for you. Right. Could you try to recover the type of flip-flop given this timing diagram? So this is a flip-flop with 2 inputs, right? But I'm camouflaging them a little bit. So they could be SR, they could be JK. Could you figure out which flip-flop it is by analyzing the waveform? Well, actually, I'll do the first example right now, and then you can probably try the second one. So this flip-flop is a positive edge triggered flip-flop, so it will only be sensitive when my clock changes from 0 to 1. And at that moment, my mysterious input, I'll call them A and B. Right? So at the first moment, A is a 1, B is a 0. My Q goes from 0 to 1. And that looks like either a set or toggle operation. Right? But 1, 0 was not a toggle operation for any of the flip-flop, so it's probably the set operation. At the second positive edge, the first flip-flop input is a 0, second flip-flop input is a 1, and my Q goes from 1 to 0. At the third time instance, both flip-flop inputs are 1s, and my Q goes from 0 to 1, and that can be explained as the toggle operation. And this one actually matches the behavior of a JK flip-flop. Right, I did some sampling in the timing diagram to figure out what is the flip-flop inputs at the positive edge, and then try to map it into some of the known operations. 1, 0 is a set. 0, 1 is a reset. 1, 1 can be justified as a toggle, and that matches the behavior of a JK flip-flop. Could you try the second one? Yeah, just keep a record of what is the flip-flop inputs at those 2 places before the edge, and see if it matches any of our flip-flops. If anyone needs some help, just let me know. Yeah, I can provide more clarifications. Hamza, any questions? Or I see. You're just tracking those signals. Yeah, with those dotted lines, it's pretty easy to see what are the input values. Right? And you want to see if that matches the behavior of any flip-flops or not. The answer is probably not. Take a look at that last 0, case. Right, 0, make it go from 0 to 1, and it doesn't match any of what we learned. Cool. Did you find something?
Sets it to 1. 0 toggles it.
Yes. That's right. Yeah, and it's now of what we learned, right? 0 doesn't do toggle in both SR and JK, so it's probably some novel flip-flop. It's actually like a typo in the textbook. The book calls it an SR, and they're trying to provide an SR example, but they miserably failed. All right, time's up. And then again, let's do this exercise together. Could someone give me the signal value at the first instance, at the first positive edge? Give me some numbers. What happened on the first edge? Oh, yeah, for the second example. Yeah. So what happened over here? Yep. They switched the Q, the state, from 0 to 1. And that looks like a set operation. Anyone for the second instance, the second edge? A goes to 0. B is a 1. 1 to 0. Yep. What about the third? Someone give me the third. Yep. Q goes from 0 to 1. Right. And okay, so for 0, to make the transition from 0 to 1, it must do either set or toggle. Those are like the two potential operations that could transition from 0 to 1. And if you look at the characteristic table, right, 0, over here is hold. For JK, it's also hold. So it's neither of those two flip-flops. Right, this is really something new. This is probably something new. Right, you can definitely define 0, to be toggle, 1, to be hold, and then try to manipulate the NOR gate, NAND gate to really build it. But it's none of what we have seen from those 4 examples. Right, this is not an SR, this is not a JK. So I would say the name of this flip-flop makes a lot of sense. So D is like data propagation. T stands for toggle. SR stands for set reset. But JK, JK is just like 2 random letters. So here's why people think JK is called JK. There are 2 stories. Number 1, this Dr. Elwood Nelson developed JK flip-flop in the early 1950s at Hughes Aircraft Company. And this aircraft company is really another place where many innovation of semiconductor was born, because they need a more power efficient and more lightweight computing device. And then I found that one of his patents in 1951, he likes to follow this kind of A, B, C, D, F, G, H order. And A, B, C, D, F, G, H, essentially he ignored all the vols. Those are like common mathematical indices. And the next two letters that would naturally come up would be JK. Like I don't find any concrete evidence, but I think he really likes following this kind of alphabetical order. The second hypothesis is developed by Dr. Jack Kilby. He invented the first integrated circuits in 1958. By integrated, I mean he puts all the devices, transistors, resistors, capacitors in a planar surface rather than some concrete devices and then connected by wires. So see, this is like a looks kind of similar to a chip nowadays, like a very flat surface, but being able to do all the computation in this planar form. And he actually won the Nobel Prize in 2000 for his contribution in creating integrated circuits. I tend to believe in story number one. I think it's a lot more reasonable because he, like Dr. Jack Kilby, does research a lot later than when people used JK flip-flops. And this guy, Dr. Nielsen is also not a random guy. He's a student of Ernest Lawrence. Do you know who that is? Like Dr. Lawrence for like this nuclear theory. And he was a student of Ernest Lawrence and also Enrico Fermi. Both of these guys are like part of the Manhattan Project, and they were developing nuclear weapons. And Dr. Nielsen was also a good friend of Robert Oppenheimer. And he was referred to by Oppenheimer to lead one of the theoretical physics labs. So this is really a very accomplished guy, a very technical-oriented person. So I can well believe that he really invented JK. And also based on his patent in 1951, he was exploring some of these sequential behaviors, counting up and counting down using 1 bit of storage, 2 bit of storage. So it kind of makes sense that he pioneered this idea earlier than Dr. Jack Kilby. All right. So finally, a different way to describe the flip-flop behavior is by putting that into a Carnot map and then write out the Boolean expression. Essentially, we can convert a K-map to convert the truth table to a K-map by using Q as one additional input variable. And from this Carnot map, you can write out the Boolean expressions. The first one would be Q plus equals D. Second one, Q plus equals T XOR D. Third one, Q plus equals S plus R prime Q. And finally, Q plus equals JQ prime plus K prime Q. It's a way to describe the next state, the next Q value in terms of the inputs and the current state. And we're going to use this equation quite a bit for analyzing the behavior of sequential circuits. So to sum it up, these are everything we have seen. 4 different flip-flops with different operations, and these are the truth table. And you can derive also the next equation based on the K-map. So that's everything for today. We built many things. We have seen like an entirely new set of components with memory capabilities. We built gating latch from latch. We built flip-flop using 2 latches. We analyzed quite a few things, analyzed the behavior through timing diagram, and also in terms of the characteristic table and the equation of these latches. And next lecture, we're going to use them to build some components, build some like real sequential circuits. So that's everything for today. Right. Yeah. Recover.
I have a question from the.
Yeah.
How's the sent you over Slack.
Uh-huh.
Because I said like, if you find a pattern, this must be like when it's 0, then it must match with the inputs on the right here, but because it's a NAND gate. Wait, no, it's a
XNOR.
XNOR
Yeah.
gate. So these must be the outputs,
Mm-hmm.
but the ones that can match like 1 0, or at least start with 1 0, is like from my previous, which is C prime.
Actually, I don't quite understand like your table representation. Can we start from the XOR gate first?
Yeah, sure.
That's the first gate. So that's based on B and C.